Hi everybody, today we're going to finish off section 7.5 by looking at some properties and applications of the cross product. So just a quick recap. We know that the cross product is perpendicular to both of the vectors that are being multiplied using the cross product. The magnitude of the cross product is equal to the area of the parallelogram that's defined by the two vectors. So magnitude of C, the cross product, is equal to magnitude of A times magnitude of B times sine of theta. And we spent some time last time going through a derivation of how to do the cross product in Cartesian vectors. So the cross product, as you can see, when you're calculating it using Cartesian vectors, is more work than the dot product. It's about 50% more work if you actually total up the multiplications and subtractions that you have to do. You do have to be careful to get the subtractions in the right order, and that's why we have the IJK mnemonic, or we use the determinant to determine the cross product. Let's look at some properties of the cross product. The first thing, we've already seen this, is a consequence of the right-hand rule. The cross product is anti-commutative, so if we cross A vector and B vector, that's opposite B vector cross A vector. You can see that using the right-hand rule. The distributive property works. That was demonstrated last time too. So if we have A cross B plus C, then this expands properly to A cross B plus A cross C. We haven't proven that, but we have demonstrated that it does work. If we assume that's true, even though we haven't proven it, then we can show that the reverse order works as well. And by that I mean if we do A plus B cross C, we can take what we know and prove that that does expand properly too. So using the anti-commutative property, this is negative C cross A plus B, which we know how to expand because we just are assuming that that distributive property works. So this is going to be negative C cross A minus C cross B, and this is equal to A cross C, again taking advantage of the anti-commutative property, plus B cross C. So that expands the way we expect it to. One thing you have to watch out for is the cross product is not associative. It does matter which pair of vectors you're crossing first. So in general, A cross B, then crossed with C, is not the same thing as A crossed with the result of B cross C. Fortunately, scalar multiplication of a cross product is associative. That means if we have K times A cross B, that's the same thing as K times A crossed with B, and that's the same thing as A crossed with K times B. So fortunately, a scalar we can put in any order. Final useful property of the cross product is we get the zero vector as a result of the cross product if and only if vector A and B are collinear. So that means that A is parallel to B, or equivalently A is some scalar times B. And this means that if we cross a vector with itself, we always get the zero vector. Let's look at some examples of using this. I want to do example 3, prove the same thing, but do it in a different way. So it is worthwhile for you to look at example 3 and see how the textbook uses Cartesian vectors. But we can also prove it using geometric vectors. So example 3 asks us to prove that property that if we have non-zero vectors A and B, the cross product is equal to 0 only if and only if A and B are collinear. So we have to prove it both ways. Let's say A and B are collinear. That means that the angle between them and I want to just split this in half. Theta is equal to either 0 degrees or 180 degrees. So the vectors are pointing in the same direction or they're pointing in opposite directions. That means the sine of the angle between them is 0, because sine of 0 degrees or sine of 180 degrees is 0. And thus, magnitude of A times magnitude of B times sine theta is equal to 0. But that is the magnitude of A cross B is equal to 0. And the only way we can have a magnitude being 0 is if the vector itself is the 0 vector. So if A and B are parallel, that means the cross product is 0. We can do the reverse as well, and it's going to look very similar, but you'll see that there's no other way it can happen, and the result is we have if and only if. If the cross product is the 0 vector, then that means that A cross B, the magnitude of A cross B is equal to 0. And that means that magnitude of A times magnitude of B times sine of theta is equal to 0. But we know by definition, because A vector and B vector are not the 0 vectors, that their magnitudes are not 0. And therefore, the only way that can be 0 is for sine of theta to be 0. And that means theta is equal to either 0 degrees or 180 degrees, and that in turn means the vectors are collinear. It's an if and only if. The only way to get a cross product is if you're crossing two collinear vectors. And if the vectors are collinear, then that means the cross product is going to be 0. So we can use that as a way to prove collinearity. Example 4 is more applied. We have seen that two vectors in 3 space define a parallelogram, and we can find the area of that parallelogram. Remember that the area of the parallelogram is equal to the magnitude of the cross product. Now, if we knew the angle between those vectors, this would be pretty easy. We would find the magnitudes and multiply by the sine of the angle, but we don't. So we have to find the cross product. So first of all, A cross B, and I will use the determinant form. So A is 4, 5, 2, B is 3, 2, 7, and I do prefer to write the differences because I find it difficult for some reason to just do the mental math consistently. So 5 times 7 is 35. We subtract off 4. Then we do 6 subtract 28 and 8 subtract 15. Carry those subtractions out, and we end up with a vector that's clearly going to have a very large magnitude, which is appropriate because we expect the parallelogram area to be large. So now we need to find the magnitude of that vector. This is straightforward. We're going to have 31 squared plus negative 22 squared plus negative 7 squared, and do the math. That works out to square root of 1,494. And that's the area of the parallelogram. And you can get a decimal approximation for that if you want to. The second part of example 4 asks us to find the angle between the two vectors. And we can actually say, let's find all the interior angles of the parallelogram. The textbook uses the cross product. Don't ever do that. It's more work, so there's more room for error, and it gives an ambiguous result. There are two angles between 0 and 180 degrees that will give you the same sine ratio. And so you have to figure out which one is actually correct. It's much easier and more reliable to just use the dot product. So we're going to use the dot product. Remember that A dotted with B is equal to magnitude of A times magnitude of B times cosine of theta, and we can isolate theta in there. Now we do need the dot product, so let's find A dot B. This is relatively straightforward. And we get 12 plus 10 plus 14, so that dot product is equal to 36. We need the magnitudes, and magnitude of A is going to work out to square root of 45. Magnitude of B is going to work out to square root of 62. So we can find the angle. If we isolate theta there, then theta is equal to the inverse cosine of A dot B all over the product of the magnitudes. Substitute in. It's going to be 36 over root 45 times root 62. And you can evaluate that on your calculator, and that turns out to be about 47 degrees. And then the other interior angle is going to be the complementary angle to that. The other interior angle will be 180 degrees minus 47 degrees, which equals 133 degrees. If you want, you can draw that up on GeoGebra, measure the angles, verify it's correct.